At roughly 85,000 feet above the Nevada desert, the air outside the cockpit is thinner than anything a human lung could use. The temperature has dropped to somewhere around -56°C. The aircraft is moving at 3.2 times the speed of sound, which means it is covering a mile every 1.9 seconds. From the ground, if you could hear it at all, the sound would arrive long after the plane had already gone. The skin of the aircraft has been heated by aerodynamic friction to temperatures approaching 316 degrees Celsius, hot enough to burn unprotected skin on contact. And at the very front of each engine nacelle, a narrow metal spike points into the onrushing air like the tip of a spear. That spike is not decorative. It is not a radome or a sensor housing. It is one of the most consequential pieces of geometry in the history of aviation engineering, and almost nobody outside the profession understands what it actually does. Here is the question that most people never think to ask. A jet engine is fundamentally a device that swallows air, compresses it, burns fuel in it, and throws the result backward. But the compressor inside that engine, the spinning stages of blades that squeeze the incoming air, cannot function if the air arrives at supersonic speed. The blades would be destroyed. The airflow would separate and stall. The engine would stop producing thrust, or worse. So when an aircraft is flying at Mach 3.2, something has to slow the air down before it reaches the engine. That something is not a filter or a fan. It is a controlled series of invisible pressure waves in the air itself. By the end of this, you will understand exactly how that works, and you will understand why the shape of the inlet that makes it possible is not just counterintuitive, but almost the exact opposite of what common sense would suggest. To understand the trick, start with what happens when any object moves through air faster than sound travels. Sound is a pressure wave. It propagates outward from any disturbance at roughly 340 meters per second at sea level, and somewhat slower at altitude where the air is cold and thin. When an object moves slower than that, the pressure disturbances it creates travel ahead of it, gently warning the oncoming air to step aside. The airflow has time to curve smoothly around the shape. This is the world of subsonic flight, and it is why a commercial airliner can have a broad, rounded engine inlet. The air is already beginning to redirect itself before it even arrives. At supersonic speeds, that warning system collapses. The object is outrunning its own pressure signal. The air ahead has no information that anything is coming. When the airflow finally encounters the surface of the aircraft, the adjustment happens almost instantaneously, in a layer so thin it is measured in fractions of a millimeter. That layer is a shockwave. And this is where the physics becomes both elegant and brutal. There are two fundamentally different kinds of shockwaves, and choosing between them is the central engineering decision in supersonic inlet design. The first kind is called a normal shock. Normal in this context means perpendicular, the wave stands at a right angle to the incoming airflow. A normal shock is the most abrupt transition possible. Air passing through a strong normal shock at Mach 3.2 does not slow down gracefully. It crashes into subsonic speed all at once, and the laws of thermodynamics extract a severe penalty for that abruptness. The total pressure of the airflow drops dramatically. Engineers measure this as pressure recovery, and a single strong normal shock at Mach 3.2 can reduce pressure recovery to roughly 32%. The engine receives air that has lost more than 2/3 of the pressure energy it started with. That is an enormous efficiency loss, and it explains why simply pointing a round tube into supersonic airflow, which is what a naive inlet would amount to, produces an engine that can barely function. The second kind is called an oblique shock. This is the key to the whole problem. An oblique shock forms when the airflow is turned gradually by a surface at an angle rather than being stopped dead. Each oblique shock slows the air down only a little, turns it slightly, and extracts a much smaller pressure penalty than a normal shock of equivalent total deceleration. If you arrange several oblique shocks in sequence, each one bending and slowing the air by a modest increment, you can bring a Mach 3.2 flow down to near sonic speed with a pressure recovery of roughly 80% or better. The engine receives nearly 4/5 of the original pressure energy. The difference between 32% and 80% is the difference between an aircraft that can barely reach its design speed and one that can cruise there continuously. This is where the spike comes in. The conical spike at the front of the SR-71 Blackbird's inlet, formerly the Lockheed A-12 and its derivatives, designed in the late 1950s and into the 1960s by a team working under extreme secrecy, is precisely shaped to generate a sequence of oblique shocks at the aircraft's design cruise speed. The cone's half angle was chosen so that the first oblique shock forms at the tip and trails back at an angle that directs the airflow toward the inlet lip. A second oblique shock forms at the lip itself. Then, only at the very entrance to the internal duct, a final, much weaker normal shock brings the airflow to fully subsonic speed. By that point the Mach number ahead of that terminal normal shock has been reduced enough that its pressure penalty is small. The system is called a mixed compression inlet, because it uses both the external oblique shocks and a final internal normal shock. At design cruise, the whole sequence is almost ghostly in its efficiency. But the spike is not fixed. This is where the engineering becomes genuinely remarkable, and where a hidden vulnerability also lives. The correct position of the spike, measured in inches along the engine axis, changes with the aircraft's speed and altitude. At lower supersonic speeds the shocks form at different angles. At higher speeds, different again. The SR-71's inlet spike was designed to translate forward and backward hydraulically, and the inlet itself incorporated movable bypass doors and a variable throat. The entire system was governed by an analog control computer that tracked aircraft speed, altitude and inlet pressure ratios, and repositioned the spike continuously to keep the shockwave system correctly aligned. The throat of the inlet, the narrowest internal point, had to remain precisely positioned relative to the terminal normal shock. If it did not, the system experienced what engineers called an inlet unstart. An unstart is the inlet's equivalent of a catastrophic stall. If the terminal shockwave is expelled forward out of the inlet throat rather than held inside it, the entire inlet goes from highly efficient mixed compression to a blunt, poorly organized shock structure in a fraction of a second. The pressure and thrust from that side of the aircraft drops suddenly and severely. At Mach 3, a violent yaw that instant is the result. The aircraft snaps sideways with a force that has been described by SR-71 pilots as feeling like being hit by a truck. The early inlets were prone to unstarts, and crews learned to expect them and respond immediately. By the aircraft's operational maturity, the digital control system reduced unstart frequency significantly, but the phenomenon was never fully eliminated. It is a reminder that holding a set of invisible pressure waves in a precise geometric position, inside a duct moving faster than a rifle bullet, across varying conditions of altitude and Mach number, is not a problem that fully surrenders to engineering. Which of these two failure modes would you least want to experience at 85,000 feet, a complete engine flameout, or an inlet unstart? Leave your answer below. The SR-71 pilots who flew both would likely have an opinion. Here is the false belief that most people carry about supersonic inlets. They assume that a sharper, more pointed nose is a designer's aesthetic choice or perhaps a drag reduction measure, that the pointy shape is mainly about cutting through air more cleanly. That is exactly backwards. The sharp geometry of a supersonic inlet is not about reducing the disturbance the inlet makes in the air. It is about creating a very specific, very controlled disturbance in precisely the right place. The oblique shockwaves the spike generates are not something the engineers are trying to minimize. They are the mechanism. They are how the inlet does its job. The shock train is not a byproduct of the shape, it is the purpose of the shape. Here is how you explain the trick to someone who has never thought about it. A round inlet at supersonic speed tries to stop the air all at once with one brutal normal shock, and wastes most of the pressure energy in the process. A spiked inlet breaks that deceleration into several gentle steps using oblique shocks, keeps most of the pressure energy, and delivers air the engine can actually use. The spike does not cut through the air. The spike organizes the shock waves that do the real work. There is something quietly astonishing about the fact that the engineers working on aircraft like the SR-71 were, in effect, sculpting invisible structures in the air, pressure discontinuities a fraction of a millimeter thick, held in precise geometric relation to a moving metal surface, controlled by a computer the size of a suitcase, at speeds no other operational aircraft has matched before or since. The shape you see on the outside is only the template. The real machine is the pattern of shockwaves it generates, which no camera has ever really captured, and which most passengers flying beneath that altitude today have never thought to wonder about. The machines that move the modern world are stranger than they look. Subscribe.